So some of you have maybe played around with this filter before, where you invert an image. It looks kind of scary, but I think basically it's like the opposite of each pixel. And what we're going to look at today is inverting functions. So functions and their inverses are basically exact opposites. They kind of undo each other. And so we're going to explore how those are connected today. Before we get started looking at these inverse functions, just like inverted images, I have a quick magic trick for you. Okay, so you ready? It's very impressive. So first of all, think of a number in your head between 1 and 10. All right, next, add 3 to that number. You got it? Okay, and now subtract 3 from that number, and you're back to your original number. Boom, I guessed it, magic. I've got another one for you. Ready? Think of a number between 1 and 10. Okay, now square that number. So do your number squared. Okay, now square root what you just got. Boom, you're back to your original number. I'm magic, I guessed it. Those are very lame, sorry. But the point I'm trying to make is adding and subtracting are inverses of each other. They undo each other. Squaring and square rooting are inverses of each other. They undo each other. In math, we often have operations that undo each other. And so when we talk about inverse functions, that's kind of what we're looking at. An inverse function is just a function that undoes the action of another function. And here is an example of 2 inverse functions. All right, so take just a minute, pause the video, and think about what you notice about these 2 functions. So we have the purple one here, and we have the green one here. So pause and see what you notice. So here are some things that maybe you noticed. First of all, they're a mirror image of each other. Like if you were to reflect this one, you would get this one. You also may have noticed that some of these points match up. For example, on this purple function, we have the point -4, 0, whereas on the green one, we have 0, -4. It's flipped. Same thing with like 0, 2, and 2, 0. They're flipped. Maybe you notice some other things that you want to share. Feel free. So here is some properties of inverse functions. First of all, if we have a function f of x, we refer to its inverse as f inverse of x. That little -1 is not actually an exponent, so I know that's confusing because it looks like one, but it's a little -1 written right by the f. It means the inverse of f. Inverses, like you may have noticed on that previous picture, they're always symmetric about the line y equals x. If you remember, that's a diagonal line where the x values and y values are equal. It's this line right here. It goes through 1, 1, and 2, 2, and 3, 3, and it goes through -1, -1. It's this diagonal line. Whoops. Because it's literally where y equals x. So inverses basically flip x and y, and so they are symmetric about this line. And so if in your function you have the point x, y, in your new inverse function you're going to have the point y, x. For example, you saw on this previous one, if we had the point 0, 2 in our original function f, then in our inverse function we would have 2, 0. It's just flipped. That is always the case with inverses. And see how this is a reflection across the line y equals x? So we're going to start by looking at tables, because honestly this is probably the easiest one. If I have a table that looks like this, here is my function. I have x values and y values, and if I want to know the inverse table, so let's say that this is f of x, oh sorry, if that's f of x, this is going to be f inverse. All I have to do for my inverse table here is flip the x and y values. If this function has 4, 11, then this function has 11, 4. Just flip them. Don't make it negative. Don't get crazy. Just change x and y. So if this one has -2, -1, we'll flip them. The inverse has -1, -2. If this one has 0, 3, this one has 3, 0. And if this one has 2, 7, this one has 7, 2. That's all there is to tables. You just flip the x and y values. So this would be our function f. This would be its inverse. Sometimes functions don't have an inverse, and so if they do have an inverse, we call it invertible. So that's what that word means there. This problem says the function f of x is invertible, so it has an inverse, and we want to find the inverse when its x value is -52. Notice there's a -52 in the table, but that's that output value. So if this is the function f of x, then my inverse is going to be this table, but flipped. So basically, if the function f has the point 52, -52, then if we flip those, this function will have -52 and +52 because those changed places. So the question asks, find the output if the input is -52. And so here's the input to my inverse function, and then there's the output, 52. So it's almost like working backwards from the original function. So the answer to this would be 52. We're going to now go through a few graphs. So taking a look at these graphs, all I want you to think about is, are they inverses or are they not? And with a graph, remember, first of all, if this is the point like 2, 0, then this one should have the point 0, 2, and they should also be a reflection across that y equals x line. Do you see how at each point, these are they're like the exact same distance away from that center line? Like if I were to fold these two graphs, they would come together if I were to fold it right along that y equals x line. This means that they are inverses of each other. Same thing here, this little double helix looking thing. The red one and the blue one are inverses because they're a reflection of each other across the line y equals x. By the way, this is the function x cubed and the cube root of x. Those undo each other. These are not inverses. So, for example, you see how there's a big parabola here and there's a smaller parabola here? Those are both parabolas, but it doesn't mean they're inverses. They would have to be a reflection across the line y equals x. Like I would have to take this parabola and basically flip it over here. So those are not inverses. Same thing here, just because these are both lines doesn't make them inverses. It has to be a reflection across the line y equals x. If I were to take this red line and flip it, it would look something like this. If I were to flip it across, it would not look like the black line there. So those are not inverses. You can also tell because like this one has the point -1, 0. So the other function should have the point 0, -1, and it doesn't. Sorry, my line y equals x was off there. I didn't see the scale, but you get the idea. All right, hopefully you can see these. Take a second, pause the video, and try to tell if these are inverses or if they are not. All right, so these two, these are inverses of each other. They're a reflection across the line y equals x. So those are inverses. Sorry if this was confusing, but this right here is a separate function, and this right here was a separate function. It's kind of hard to tell. But those are also inverses because they're a reflection of each other across that line. These two are clearly not. They don't even look the same. So these two are not inverses because they're not a reflection across the line y equals x. Again, pause the video and see what you think about these two. Are they inverses or are they not? These two are. It's a reflection across y equals x. These two are as well. It's a reflection across y equals x. Here's a couple more. Pause the video and see what you think about these. This is a line and then a curved function. Those are obviously not inverses. You can't reflect one and get the other. These are also not inverses because if I were to reflect across this line, I wouldn't take this and get this, or I wouldn't take this and get this. Just a couple more. Okay, so these two parabolas actually are inverses of each other because if I have the line y equals x, this diagonal line here, do you see how at each point they're exactly the same distance apart from that line? So those are inverses. These are two parabolas that it's a translation, but it's not a reflection across the line y equals x. It has to be a reflection across that diagonal line, and these two are not. So those are not inverses. I want to come back to number 8 really quickly. Oops, sorry. So on number 8, this is a bit of a side note, but remember how one test that you can use to see if a function is actually a function is you can do the vertical line test, as in run a vertical line through your function, and if it ever hits 2 points at the same time or more, it's not a function. This blue parabola here is a function because it only hits 1 point at a time as you pass that vertical line through the graph. When we talk about inverses, inverses often use the horizontal line test because if I were to run a horizontal line through this function, I only want to hit 1 point at a time, and that would mean that the original graph is a function. So that's just a side note. You don't really need to dig too much into that, but I thought I'd throw that in there.